Okay, good morning, everybody. This morning we have our first talk online by Ionut Chifan, and he will talk about rigidity results for group von Neumann algebras with diffuse centers. And we'll try to keep an eye on the chat for you, Ionut, and as well questions in the audience. So please go ahead.
Okay, so can we see? Okay. So first of all, I would like to thank very much Lisa and David for giving me the opportunity to give this talk here. This has been a very nice workshop so far, at least the talks that I follow online. So thank you very much for the opportunity. Yes, in my talk, I will be talking about the rigidity results for group von Neumann algebras with diffuse center. So I'm going to report on some new results in this direction, which I obtained working with my student Adriana Fernandez Cuero and Huitan. Okay, so in the first part of the talk, I would like to introduce the objects that we'll try to classify. So this talk is about classification of some von Neumann algebras, which are associated with groups. So I'm going to introduce my objects. I'm going to survey a little bit some of the results that are somewhat landmark in the area, and then I'm going to introduce the actual results that I want to talk about. So first, let me very briefly recall what a group von Neumann algebra is. I think probably most of you know that, but doesn't hurt to do this. So in my talk, we will typically deal only with countable discrete groups. So every such a group admits a left regular representation, right? And the group von Neumann algebra associated with this group, it's essentially the left regular, the von Neumann algebra generated by the left regular representation. So in essence, every element of G induces a translation operator on the square summable functions on G, right? And if you take the linear span of such operators, this forms a copy of the group ring, which is represented in the bounded operators over L2 of G. And then we just simply take the, strong operator topology closure or weak operator topology closure, or whatever you prefer. And the resulting object, it's what we call the group, the von Neumann algebra associated with the group, okay? Now, a few basic facts about this object. So a group von Neumann algebra admits a faithful normal threshold state by just simply, you can check that for every operator like this induced by a group, you are just associated the Dirac at the point G. So it is 0 if G is not the identity element of the group, or it's 1 otherwise, okay? Now, because the algebra admits such a state, or threshold state, faithful threshold state, that implies automatically the von Neumann algebra. It's a finite von Neumann algebra. Okay, so that's very nice. Now we know some other basic things is that this von Neumann algebra, it's what we call a type 1 factor, specifically when the group, all the non-trivial conjugacy classes of the group are infinite. Okay, that will refer throughout this talk at the ICC condition. Okay. Now, another thing that you may have, and this is more generic, does not necessarily pertain to group von Neumann algebra, but a type 1 factor. So you're going to see throughout this talk this notion of amplification of an algebra of a factor. So M is a type 1 factor. So it just simply means that a von Neumann algebra which admits such a faithful normal threshold state and has no cannot be decomposed non-trivially as a direct sum of 2. That means that center consists only of the scalars. So if you have such an object, for every projection in your algebra, you can compress your factor and you get another type 1 factor, which is going to be denoted by PMP, okay? And it's a fact that the isomorphism class of this compression essentially does not depend on the projection itself, but it depends on the value or the valuation of the trace on this projection, which is essentially a number, okay, a positive number, okay? between 0 and 1. Okay, so that's in the situation when P, it's just a projection, but you can also define other amplification when this T, it's actually a number above 1. Okay, I'm not going to go into the details of that. But the point is that this isomorphism class of this, we're going to denote it by M to the T. So you're going to see during this talk, this type of notation. Okay. Now, of course, there are many properties that these algebras have. I'm not going to enumerate them here, but I would like to talk a little bit about a classification program within this framework. So what we like to understand, it's a fundamental question. It can be traced to the pioneers of the field, where people try to understand how the object L of G depends on the underlying group G. Okay, so specifically, we'll try to classify this object in terms of the group. Okay, in other words, what algebraic properties of a group are retained by the von Neumann algebra. So just looking in the isomorphism class, you can recapture those properties. Okay, so that's one relatively big thematic that kind of drove all the research in this area over the years. Another question that I'm not going to talk too much about it, but it's going to appear and there will be results that will play a role in this direction, are the computation of symmetries. I think this kind of plays well with the thematic of this workshop. So specifically, we want to understand computation of symmetry, so the outer automorphisms of your object. And another thing is the fundamental group. Of course, fundamental group, it's essentially all the real numbers such that the T amplification of LG, it's isomorphic to L of G. Or in other words, you can think of, you want to record all these projections for which the algebra, it's isomorphic to a proper corner by that P. Okay, this typically it's formulated in the framework of factors. Okay, so type 1 factors. So this is where we studied these symmetries. Okay, but the classification, the structure of L of G typically can apply to any group, doesn't have to be necessarily an ICC group, and that will be precisely the purpose of this talk. Okay, now a few things that we can point out that this object is notoriously difficult to classify, the group von Neumann algebra, and this kind of surfaced from the beginning of the inception of this field. For instance, a basic observation is that if you start with any infinite abelian group and you create this group von Neumann algebra, you always going to get an abelian von Neumann algebra, diffuse abelian von Neumann algebra, and these are all isomorphic to L infinity with 0, 1 with the Lebesgue measure. So you see that clearly that if you vary this group, the object, the isomorphism class does not retain anything about G. But you may say, well, this is maybe something only about things with center or abelian. How about the factor case? Well, factor case was, equally from the beginning it emerged that does not retain much of this. So this was present already in the work by Murray and von Neumann. So in their work, they introduced this, what we call approximately finite dimensional type 1 factor. So this is essentially a tower of finite, a factor, it's approximately finite dimensional. It essentially can be represented as a tower of finite dimensional algebra whose union is dense. It's also T dense in the whole factor. Okay, so you can formulate this in general, right? And it turns out that this is unique. Okay, always you get the same object at the end. So in particular, if you start with a locally finite ICC group, so group is a tower of finite groups, then automatically you get always a von Neumann algebra or a factor, type 1 factor, which is isomorphic to this approximately finite dimensional factor. But this can be pushed even further. In fact, one can take any amenable group, okay, any amenable ICC group. So if you create this von Neumann algebra, you always get something isomorphic to Murray and von Neumann approximately finite dimensional factor. So amenability, I suppose most of you know what that means. So it just means that it's an analytic property. It just means that essentially the left regular representation has more and more invariant vectors. And this is a huge class of groups. It covers all the abelian, solvable, locally finite, is closed under extension, subgroups. So it's a huge, uncountable family of groups. Okay, and they all give you, if you take something ICC, they always give you the same object. Okay. Now we can combine the two results, and this one and with Kwon's result, and actually you can say that even if you take algebras which are neither factorial nor abelian, right, you still have this lack of remembering anything. So, for example, if you take any abelian infinite group and any ICC amenable group, you take the direct product between them. This von Neumann algebra that are associated here will always be isomorphic to this von Neumann algebra of L infinity of 0, 1 tensor, the AFD, right, or the approximate finite dimensional factor. Okay. So only later, right? So from the beginning, the field was. All these results, in the one hand, they can be seen as classification results, but also they seem that it seems to be very hard to actually identify situations where actually the algebra retains something about the group. Okay, and the first sign of rigidity, as we like to call them, kind of emerged from the work of Kwon. Of course, there were other examples where people could distinguish between group von Neumann algebras, but I'm not talking about here in particular is this, this family of groups introduced by McDuff. But I'm not going to talk about that. However, in the 80s, Kwon kind of discovered something very, striking somehow. It's easy, but also striking is that if you take groups which are kind of very opposite for the amenable groups, so in particular property T, ICC groups, then their von Neumann algebra manifest. Show a little bit of or manifest a rigidity, namely that the symmetry, there are only countably many symmetries for this algebra. So this group factor. So the auto-automorphism group and the fundamental group, they are both countable. And this depicts a very stark contrast, for instance, for the amenable case. I didn't write it in the slide, but if you take J to be amenable, the auto-automorphism group and the fundamental group, it's are huge groups, right? Auto-automorphism group, it's huge. You can embed pretty much everything there. And the fundamental group is the whole R plus, okay? So this basically with a kind of pigeonhole principle argument, right? The analytic framework, he could show that this have meet only countable symmetries. Now, if you do not know what property T group is, fine, we can very briefly review it. So like I said, it's an opposite property with amenability. It just means that a group has property T, specifically whenever you have a unitary representation, which almost has invariant vectors, so I have this kind of vectors that become almost invariant for the representation, then naturally need to have a non-zero invariant vector. So for example, you see that if a group is amenable, it has property T in the same time, that those groups necessarily have to be finite, because being amenable, if you need to have almost invariant property T, then property T will force this to have an invariant vector, but left regular representation has an invariant vector, non-zero invariant vector only when the group is finite. Okay, so this is kind of a very disjoint class, right? Okay, and now we can see that there are many natural groups with property T, lattices in higher rank Lie groups like SLN, PSLN, uniform lattices in SPN1, which then it's at least 2. This is what we like hyperbolic case. Also, another property that will be extensively used during this talk is that the property T actually passes to quotients. Okay, amenability also passes to quotients, but okay. So all these things kind of underline that it's pretty difficult to classify this type of this is the moral, right? So we have some results, some rigidity results. But then in 2001, Poppa introduced this framework, the formation rigidity framework, right? So this comprehensive theory to try to kind of combine together analytic, geometric, representation properties of groups and such. And through this mechanism, many situations emerge where actually you can retain a lot of properties, algebraic properties of the groups from their algebras. So here I'm not, there's been hundreds of papers written about this, but I don't have time to go into this, but just to exemplify, I'm going to point out some results in this direction just to show that actually classification can have successful answer if you look in the right places, right, for the right classes of groups. So one such class for which have been a lot of progress is this class of generalized wreath product groups. So if you have a group A and another group B together with an action somewhere, just an action, then you can associate the generalized wreath product with A by this, which is just simply the semi-direct product between the groups, the group of all finitely supported functions from I into A. That's how you think about this, or if you like, direct sum, right, of A along I, it's the same thing. Okay, and then obviously B acts through this folded direct sum through the action, shifted the indices to the action of B on I, right? Okay. Yeah, something like this. And, you can take the semi-direct product, and this manifests a lot of rigidity properties. For example, there have been obtained a lot of results here, some of them which are, in my view, are landmark. One of them is Popa's result from 2003, which asserts that if you take two wreath products, okay, so these wreath products are called regular when I it's equal to B. So that means that when instead of taking an action, you just take an action of B on itself by left translation, okay? And in that case, we obtain what is called a regular wreath product, and which will be just denoted by this, okay? Okay, so in this context, with assuming some properties, some rigidity properties on the acting group. So, for example, if B and D are two property T groups, like the one that we described, two SLNs, for example, or maybe PSLNs if you are in the ICC, the von Neumann algebra associated to these wreath products, right, with Z by this B are isomorphic. If they are isomorphic, then basically the acting groups are isomorphic, right? So this sometimes is viewed and called a relative version of the convergent conjecture, okay? Okay, then, exploiting various properties and various aspects of this groups, choices for B and so on, through this mechanism or this class of groups, have achieved situations where you can obtain fundamental trivial groups. So that means the trivial fundamental group, that means that the group factor is not isomorphic to any of these non-trivial corners. Or even more impressively, you can compute the symmetries. The symmetries essentially come only from symmetries of the underlying group and multiplicative characters of the group. So this is a formula that was conjectured to hold by Jones, some many years ago, right? Like 23 years ago, it was conjectured to hold for all property T groups, sites of property T groups. Of course, this is not this. Examples here will not be property T, but somehow it reveals situations where one can expect such very powerful calculations. Moreover, in a work by Stefani and Sorin, basically, Pop and Vass show that any finitely presented group can be occurred, using this type of formula plus some geometrical theory development. That in fact any finitely presented group can be realized as the symmetries, right, of the outer automorphous group of a type 1 factor. And even more impressively, in 2010, emerged the first examples of groups which are W star superrigid. So that means that if L of G, so L of this particular, it's a very specific type of wreath product construction. In some sense, is functorial on these subgroups of this B, but the construction itself, it's of a particular kind. And superrigidity means that the group von Neumann algebra of this completely retains the group. So if you have that L of G is isomorphic to L of H with some H, with no assumption on H, then this H has to be that G, okay? Okay, so these are kind of, these results here emphasize that there is possible, and, all the work that have been done so far shows that it is possible to obtain very strong classification, lots of situations where you can recover entirely your, discrete information that you started with on the group, from the Neumann algebra. But now, for the purpose of this talk, I would like to look into the complementary situation, or the situation where the group essentially it's not ICC, and not only that, but the von Neumann algebra has a center which is diffuse. Okay, so this is the purpose of my talk. There are very few results in this direction. Typically, it's are quoted like, well, if you solve it for factor, we're going to solve it for this, but it's not quite what I have encountered studying on this. So I think it's an interesting problem. It's an interesting theme to study, right? And it's possible to reveal some new connections and to spark some new technology in this direction. So let me, in order to introduce the results that I want to talk about, I'm going to review again the class of real-like product groups. So this is an object that we have introduced together with working with Adrian, Ioana, Denis Osin, and Bin Sun. Okay, so what is a real-like product group? So this is kind of like a generalization of the notion of wreath product group, the ones that we have seen before. So again, we start with two groups, A and B comes equipped with an action somewhere. Then we say that G is a generalized wreath product, okay, of A and the action, and will be denoted in this way. So I'm going to emphasize the group, which is basically the base group, this A, and this action in this way. And we say that G is a generalized wreath product if basically G occurs as an extension. So if there is a short exact sequence between this group and B, okay, as written in the slide, which the only, with the only assumption that you require is that the action by conjugation permutes the factor. So basically, because this group is normal in G, obviously the action by conjugation by element in G on this group, there is an action of conjugation like this. And what I'm saying is that if I take an 8 label copy, so all these A's are basically copy, isomorphic copies of A. Right? And if I take AI and I conjugate it by any element in G, I'm going to get another copy of A, specifically, which is kept on track by this index, right? So specifically the 8 copy. So what you do, we're going to take the element G. This is going to be mapped by epsilon G into B. Now B acts on I, and I'm specifically asking that the I copy is moved into A epsilon G acting on I. Okay. Okay, now how is this different from the generalized wreath product that we talked about it before? Well, it is different because I never assume that this extension splits, right? If this extension splits, then it will be exactly that, okay? So I'm allowing that there is a two cocycle somehow associated to this that can enter the game. And this might seem like a small game to play, but it turns out that it has a lot of structure and, reveals an object that could help us to make progress on a lot of problems. Okay. So why we consider such things? So I'm going to take this perspective, the geometric group theory perspective, to show that, or to emphasize that there are many wreath-like product groups that one can construct from geometric group theory. Okay, and I will show in just one slide how, for instance, what is the perspective and how this basically gives you the actual generalized wreath product, the one that are split, right? So, for example, if you start with a free product of two groups, A free product with B, so I'll assume that G, this is my group, then one can see that the normal closure of A inside this group is nothing else but all the possible conjugates. So now, since I talk to group theorists a lot now, I learned their notations, which are not necessarily in bon ton with the operator algebras, but I've been corrected all the time to do it this way. So A to the B, it just simply means that taking A and conjugating it by B, okay? Okay, so that's what I mean by that. Yeah. Okay, so if you compute this free product, you see that I can conjugate all the copies of A by the elements of B, and they are in free position. So the group generated by them, it's essentially a free product, a folded infinite free folded product. And now, obviously, G, it's essentially all the elements in the G's can be written as something in this closure times something in B. You can see actually that B acts by free shift, right, on this. And now I can take the subgroup generated by commutators, right? If I take the subgroup here, which are as a relation commutators between these copies of H the B for different B's, right? And see, then if you quotient, it's a normal subgroup, can show that pretty easily. It's a normal subgroup of G. And if you quotient by that, you're going to get exactly the read product between A and B, right? Because you are killing the free part, you are making them commute, essentially. And the action, the free action becomes the shift action by the shift, okay? Okay, and this example is actually what leads us to explore whether we can do this type of process on more general groups than free products, for example, relative hyperbolic groups, okay? And this kind of lead into this notion of Cohen-Linden subgroup, okay? So if you have a group A inside G, this is called Cohen-Linden subgroup. If the normal closure of A, it's essentially, again, a T-folded free product of some conjugates, right? For some transversal of the normal closure of H inside G. You know, H is not... okay, so this is... I think it's a typo here, should be A. Okay. Okay, so we see that this A, right, in a free product, it's a Cohen-Linden subgroup, but then we realize this has been studied a lot by Cohen-Linden, and in fact, they looked at maximal cyclic subgroups in the free groups or one-relator groups, and you know they showed some impressive results that you know any maximal cyclic subgroup is a Cohen-Linden subgroup. And then how is this relevant to build generalized real-like product? Yeah, well, through the same mechanism, right? If you take a Cohen-Linden subgroup like that, basically all these conditions are satisfied. Yeah, so having these properties and this property kind of land you here, right? And again, you can take, so basically your group is like an extension between this folded free product and some quotient. And inside this normal closure, I can take commutators between consecutive any possible, you know, different positions, right? And it turns out this is a normal subgroup of G. And if you quotient by this, you're going to get a real-like product between A as a base group, right? Guy like this, and this quotient being exactly the quotient by the normal closure of A. Okay? And proof is pretty easy. Okay? So essentially that tells us that, okay, so if you want to get a lot of real-like product groups, you'll basically have to identify Cohen-Linden subgroups in the groups that you want to study. And this connected incredibly well with this notion of geometric group theoretic den filling that has been studied a lot in group theory. It's coming from the work of Thurston from the 80s. But of course, so for manifolds, but of course, we are interested only from the group theoretic perspective. And the biggest, you know, the main result that we used to build a lot of real-like product groups in the form of quotients was, I mean, through this type of quotienting procedure is this theorem, which is a combination of many hands, I would say, work. I mean, it's the work of Wosin from 2006, and then a follow-up by Dachmanigi, Radel, and Wosin, and then more recently by Bin Sun, one of our co-authors. And essentially, what this theorem says is that you can obtain, you can play this game into relative hyperbolic groups. So if a group is hyperbolic relative to a subgroup, then inside that subgroup, you can go deep enough, right? So with finite index normal subgroups, you can suppose that you can find smaller and smaller finite index normal subgroups here. And at some point, there is a threshold, right? So if you avoid, if you're familiar with you know, with the Thurston theory, if you avoid finitely many slopes, this is what this means. So if you go deep enough, so you just have to avoid a certain finite set. And if you do that, then with the H, then indeed the normal closure of this H inside the whole group, right, is going to be a free folded, is going to be a folded free product of conjugates of this A via a transversal, right, of this inside the subgroup generated for the subgroup generated by the normal closure of A and H inside W. And moreover, the quotient that you obtain out of this, it still preserves hyperbolicity. This is specifically the den filling. This is exactly Thurston theorem and the work of Wosin, but the new things, it's essentially the fact that this kernel has this free product structure, okay? And if you basically do this quotienting procedure. So if you take the commutator, the subgroup generated by all this commutator, then you're going to get a read-like product with base A and read product the natural action of this quotient, so this hyperbolic quotient on this set. Okay, and what we did then is that we showed that essentially any hyperbolic group has this. You can build Cohn-Linden subgroups pretty much in any hyperbolic group, and you can build a free group, which is actually of any rank you want, which is actually appears as a Cohn-Linden subgroup, and then basically you can quotient by this, and the result that you get at the end of the day is that you can build a ton of read-like product groups by doing this quotient procedure of hyperbolic groups. Okay, so specifically, if you start with any hyperbolic group, then for every finitely generated group there is a quotient. Okay, such there is a quotient of W, which is a read-like product between A and B, where B is hyperbolic. Okay, so in particular, if you start with the group W, which is hyperbolic and has property T, like a lattice in SPN1 with an at least 2, and you do this procedure, right? Because I can build lots and lots of Cohn-Linden subgroups in this group, then I'm going to get a lot of read-like product groups, which actually have property T in particular. And this already tells you that this departs a lot from the classical or split read-like product groups, which basically never have property T in the interesting cases. Okay, so it's a huge class of groups, and using this we made the progress on these questions: Cohen rigidity conjecture, Jones outer automorphism problem, and more, a more comprehensive conjecture which basically contains this. So for example, so I wrote some results here. So from the last years, is that if you take any read-like product group between an abelian group and a ICC subgroup of a hyperbolic group, then if you take any property T groups like this is W star superrigid, right? So this is like Cohen rigidity conjecture, right? In other words, whenever you have a group H, which is isomorphic to L of G, then the group must be actually the original group, okay? And of course, you have even more concrete quotient, right, that I wrote here, but you can read this in the paper. So this theorem provides, because you can construct all these quotients like this, it provides uncountably many actually, or a continuum of property T read-like product groups with abelian base and property T which satisfy Cohen rigidity conjecture. Okay. More recently, we also were able to kind of establish a converse to this well-known result of Cohen, the one that I mentioned. So at the beginning, I mentioned that, so Cohen discovered that property T group factors, right, have countably many symmetries. So you can reverse one of this arrow here, namely, so through a fairly involved development in geometric group theory and also in von Neumann algebra, we can show basically that any countable group actually can be realized as the outer automorphous group of a property T factor of a specific read-like product group G, right? So if you take any C, then you can find, in fact, you can find uncountably many G's such that the outer automorphism of L of G is isomorphic to the C. Okay, now this is very involved. We have to, uses a lot of big guns in geometric group theory. So there are the regular small cancellation things, but also there is all this work by Haglund and Wise on relative on residually finiteness of hyperbolic groups and so on and so forth. So I don't have time to go into that, but I think what is interesting is that you can basically say that Cohen's result is optimal, right? Everything is countable, and any countable thing you can realize it, right, for a model. Okay. 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 So now, how about some new results in this direction? And I will point out two of them which are connected with the things that I would like to talk about, right? So the two results that I'm going to show, which basically is classification in the case of non-ICC groups, right, or algebras with center. So there are two things that you're going to see here, and this kind of, we had to establish this, but I think this is a proper time to mention them since we talked about these results. So these are results involving factors still, right? So one thing that we found interesting interesting, and it will be useful later on, is that if you take any wreath-like product group, okay, where the base group is abelian, the acting group, it's an ICC subgroup of some hyperbolic group, and the action has amenable stabilizers. So every stabilizer here is an amenable subgroup of B. Okay, so in particular, if you B acts on I, by left translation, all the stabilizers are finite. So that's such an example. So if you take any property T group in this class, and we have seen there are many of them in this class, okay, then if you take any H, any group, and any scalar two-co-cycle of this H, right? So for every group, every scalar two-co-cycle together with a countable group, you can put this information together, then you can build what is called a twisted group algebra, okay, where essentially the multiplication between unitaries will have to involve this co-cycle, this scalar co-cycle, okay? I think we have seen some of this during the prior talks, even though they were in the context of C-star algebra. You can do this more generally, but the point is that you will get a twisted group von Neumann algebra. And the point is that, so if a compression of this particular group algebra, it's isomorphic to any twisted algebra of a group, then it must be the case that compression is trivial, is done by the identity. So in other words, if you compress this L of G by any non-trivial P, there are lots of them, right? Any number between 0 and will give you such a projection, okay? Then you're gonna get something that will never be a twisted group algebra, okay? So this is what this result says, okay? That's number one. Number two, we can actually push this further away, and we can kind of classify isomorphisms, right, between wreath-like product groups. So for example, if you take two wreath-like products group G and H, right, both of them with essentially the same conditions, these conditions that A, it's abelian, B, it's ICC, and the action has amenable stabilizer. So a symmetric condition, even though the C and the D don't have to be the same, they just satisfy symmetric conditions. Okay, like this. And then if you take, suppose that for the second group also have a two-co-cycle, right? Then if you have an isomorphism between a compression, any compression, right, of this L of G by a number T, and the twisted group algebra of the second group, so if you have any isomorphism like that, then a bunch of things need to happen. First of all, the compression needs to be trivial, so the projection that you're compressing by here is 1, and this is kind of comes from the prior result, okay? But moreover, the two-co cycle that you are assuming is any two-co cycle, it's actually a two-co boundary, right? So it's some twist, right? And not only that, but the two underlying groups are isomorphic. Moreover, you can actually describe the isomorphisms, right? So the isomorphism is coming from a character, from a multiplicative character, in an isomorphism of the underlying groups, okay? So in other words, if you have your guys that naturally generate, right? This is what generates the L of G, and the VH generates the L of H, right? The canonical unitaries. This group, this isomorphism is group-like. It's coming from moving group elements to group elements through essentially multiplying, sending UG to delta G via the group isomorphism and multiply this or twisting this by a multiplicative character, okay? So not only that, it says that this is not, so not only that these compressions are not twisted algebra, but also it says that, if L of G is isomorphic to something twisted, that has to be untwisted, right? And it's actually a group algebra, okay? Okay, now finally we can introduce our results, okay? So what is the first result in this context of groups with center, right? I mean, with non-trivial center. So let me state the result and go slowly over it so that kind of try to comprehend the conditions. So first of all, again, I'm going to deal with wreath-like product groups, okay? So first of all, I will have so again, symmetric conditions as before, right? Start with a reed-like product group between which has a base, which is an abelian, an infinite abelian group. I mean, can also be finite, it doesn't matter, just not be non-trivial. That's the only thing that matters. Now, the acting group, you need to have a few more conditions. Not only that it's a subgroup of a hyperbolic group, but also you kind of have to assume that all the centralizers of non-trivial element are amenable. That's a very natural condition to consider. Most of the hyperbolic groups are like this, even though occasionally you can have pathologies that can embed in a hyperbolic group like Z2 times F2 or something like this. So you have to avoid that type of pathology, okay? Okay. And also again, as before, the stabilizers of, you have an action on this group somewhere with amenable stabilizers, okay? Now, one condition that actually plays a role in our proof is that we also have to consider not only a reed-like product with the property T like this, but they also need to have a boundless condition, right? So as we talked about, every reed-like product group, because it comes from an extension which is not necessarily split, it has a non-trivial two co-cycle, okay? And what you're assuming is that, this two co-cycle that you have here, basically it's a map from D times D with value in C to the I to the two co-cycle condition. So in particular, if you look at every element like this, it's a representation in your, as a function with finite support from I to C, and you can take the support of that function, okay? Well, now you want the support to be, the cardinality of support to be uniformly bounded, not the support. So support can change left and right, but they cannot increase more than one, right? Now, it turns out that using geometric group theory can actually, most of the results that we built before, you can actually extend them. You can always arrange for this condition to happen in a lot of them, okay? And so if you start with a reed-like property T group like this, which in addition has two more lack of symmetry conditions. First of all, you want this group to be perfect groups. So that means have trivial abelianization. Not too much to ask for because, abelianization of property T groups, it's always a finite group. So you just have to make sure that there is none, right? There. But also you want to assume that the automorphism of this group is torsion-free. Okay, so these are two technical conditions that come from the proof of the theorem. And, while I believe that you can go around them, I think the technology is not developed in this manner. And specifically where it is difficult is that, like the results that we presented here before, the superrigidity results for factors, which kind of come from twisted algebra, there is no superrigidity result in that of that flavor. And that's why we need to assume these conditions, okay? Okay, so you have a group like that, a reed-like product group with these conditions, and then I'm going to take any abelian infinite group and I'm going to take the product, A times W, okay? So in this moment, these W's are ICC groups, property T ICC groups. Now, A is just an infinite abelian group, so the group that we're going to have here in this moment, obviously, it's not anymore an ICC group, it's something which has huge center, okay? Then we want to see how much you can reconstruct from this group algebras, right? So I'm going to say that, well, now consider any star isomorphism between this group and any group with no assumption on it. And now, one of the things that kind of come, a condition that you need to assume, right, is somehow in the case of factor, it's invisible because it kind of happens all the time. But here the point is that you want your isomorphism to preserve the canonical traces. When this is a type 1 factor, this condition happens all the time. So it's in no way it is natural, okay? Okay, so assuming this, now I would like to see what properties H share with G. I mean, can I classify this? And you have basically up to the center, you have a full reconstruction. So what that means is that H itself is going to be a product between its center and some group, some ICC group. And that ICC group, it's exactly W, it's isomorphic to W, okay? So you do not reconstruct the center, you recover the fact that this is a product between something and W essentially, but that something being an abelian group can be anything, right? You cannot recover that part, via the results that we talked about. And moreover, you can write the isomorphism down. So in other words, and it's a little bit trickier than in the case when you have when it's ICC, right? So what needs to happen is that you can find a countable partition with projections in the center of the unit, right? So that you can write one as sum of countably many orthogonal projections, and for each orthogonal projection you can find a okay, sorry. And for every, when you can find an isomorphism, right? Right, between W and this quotient, you know, this part here, okay, and the unitary such that the isomorphism looks like this, right? Okay, so it's going to send essentially x times UG. These are basically generators because, you know, your L of A is a tensor, right? Algebra, L of A tensor L of W, right? So at the level of L of A, which is the center, you don't recover much. It's whatever it is in the center, can be anything. But then multiplying with these projections, right? Then you have here just isomorphisms, right, of the group. I mean, from W to this, okay? So in the situation that you could technically start to the situation when this is not just torsion free, but it is actually trivial, okay? So in that case, actually, it's only one, so there is no sum. It's actually the thing that they expect. So that's the only case where actually the isomorphism basically looks like, kind of like it looks in the case of factors, okay? And this is optimal. Every single time when you have a bunch of isomorphisms like this in a partition of the identity, you can write isomorphisms between these algebras with exactly this formula, okay? Okay, any questions so far? Okay, and finally, this is the second result that I want. You know, the rest is just discussing a little bit of the proof, ideas of the proof. But there is also a C star counterpart of this. Okay, so again, in this case, actually, the proof it's or the result is somewhat more involved, right? And you know, and also more involved, but also in the same time actually more accurate, and you can recover more because obviously sister algebras are smaller objects, so you kind of expect that. So again, so this, and this has like a double thing. It's a two case thing, right? So first of all, so suppose that again we have our assumptions that we have a reed-like product group, right? With so I have a reed-like product group with abelian base, subgroup of a hyperbolic group as an acting group, and some amenable stabilizer action. Okay, and if you pick any group which has property T and is torsion free, by the way, these conditions can always be you know, ensured, right? So I have two cases. Either W is in this situation. So here, as you can see, I'm not assuming anything about this W being perfect group or the automorphism being torsion free or anything. Just a group like this. But you have to assume that the base group, it's a finite abelian group of finite rank. Okay, it's a free abelian group of finite rank, right? So either you are in this condition about W, or you are in the prior condition, right, where you have again a property T group, and you know you are assuming that these are perfect group and has no. So essentially, this two condition means that there is no finite order symmetries of your algebra, right? But in this case, I can assume that A is any abelian torsion-free group. So it doesn't have to be free abelian or anything, just abelian torsion-free group. And then again, you form the product between this group A and this either reed-like product in this category or in this category, and you know they have property, right? Then you can describe the C star isomorphism between them. So if you take the reduced C star algebra of G, and then you take any group together with this C star algebra, you have an isomorphism from this C star algebra into this one, which preserves the trace, the canonical traces. Okay. Then in this case, automatically can conclude that H has to be isomorphic to G. So you have a complete reconstruction of the group. Okay, unlike the von Neumann algebra case where you reconstruct everything but not the center. Okay, so here you can reconstruct the center, and moreover, exactly as in the previous case, you can write down the isomorphisms, you can classify them. So as before, there is a partition of the identity with central projections. I mean projections in the center of H, and there are isomorphisms between this W, and so you know H being isomorphic, it splits as a product, right, between the center and something else, and that something else is isomorphic to this W, and there is a unitary, same formula holds. And once again, when the automorphism of W is trivial, actually there is no sum here. It's just sending X tensor IG into P of X tensor V delta G. And what I should mention in this case is that still, you know, at the level of the center, you do not have a description of phi, right? Because this is just an abstract isomorphism, right? I mean, you have a classification of this homogeneous sister algebras, but there is not a clear formula that relates how the isomorphism relates to the isomorphism between the groups. So that one kind of remains the same, that part. But you still, the group is still isomorphic. So this group is, in this sense, C star superregional. Okay? Like this. And then, of course, what I should say, just 2 words, so this is just describing the proof, right? Which one of the things that I wanted to mention is that, in fact, I think working over this, we found the framework on how can reconstruct a center of a group from W star equivalence. And what is interesting is that we do a lot of analysis at the level of the FC center. So every group has an FC center. So the group generated by all the finite orbits, right, under conjugation. And one of the things that we can prove, and I think this far exceeds the class of real-like product groups. So, I mean, you can do it for a lot of groups, is that. So, and I will just mention this and then I will stop. I mean, there were multiple things in the proof, right? Because you kind of need to reconstruct the center first. So the idea, and you're going to show that center, it's essentially this FC radical. So you have to take this FC radical and you show eventually converge to being the center. Typically, it's not the center. It's a much larger group, okay, BFC group. Okay, but first, so you cannot show it's abelian right away, but what you can show, and this involves actually a lot of analysis, and this fact that these cocycles have bounded support and all this type of stuff, you know, this is reflected in a deformation that we build for this algebra, and we can do the analysis because of this condition. But anyway, at the end of the day, what you get is that if something L of G is isomorphic to L of H like this, then this FC center, it's in fact is not necessarily the center, but up to a finite normal subgroup is the center. So namely, this commutator is finite. And I wanted to point this out because in the process of so you have this deformation rigidity argument where you exploit this deformation that you build against the weak compactness of the action. So the group H acts on the FC radical by conjugation. And this is essentially a weakly compact action in some sense. And this is the source of rigidity. And you show that basically all the groups, all the von Neumann algebra, I mean, the algebra of the FC subgroup intertwines back into the center, or a piece of it basically can be conjugated in the center. And this condition actually translates exactly into this being finite. And you basically, what you do in this proof is that you generalize an older result of Neumann from 54 on BFC group. It's a famous result that, you know, if you have a BFC group, essentially the commutator is finite. So you extend this and do analysis on orbits and things like this. And it seems that the analytic framework that von Neumann algebra gives you this, it's in fact a very powerful one, because you can prove all these generalizations, which are not obvious in the case. We couldn't find them in the literature and so on. Okay, so this is basically the first thing, but then you want to show the second step is to use the essentially the integral decomposition. So now you proceed to compute the integral decomposition of this algebra, and you use the fact this group is finite, and you can show that the fibers are essentially a semi-direct product of the quotient of this acting on finite dimensional algebras. I mean, semi-direct product like cocycle actions. Okay. So that's what you can compute. And this is where you play those results that I mentioned, right? If you compress this algebra, therefore, they are twisted algebra, but then you use the structure of this to show that the compression is trivial. So you are killing in this way this normal finite subgroup. So basically, this commutator is trivial, in which case the FC radical is the center. So you get there. And now the second layer of technicalities and proof is to show that it splits. And this is by no means easy. It's actually pretty complicated. So this is where we have to develop this rigidity comparing. So if you look now at the fiber and you're comparing group algebra with twisted group algebras, right? You have isomorphism between them, and you want to conclude that this twisting disappears. And that's how we show splitting. And then that's also not enough. You have to pass through a Serre's theorem, right? Serre's famous theorem that essentially you have a central extension, right? You have a central extension, right, of a group, and you know, if the extension doesn't split, right, then if the quotient has property T, then the whole group has property T. So you have to play with this type of techniques, right, to show that essentially you negate this and you do an iterative process, and eventually you're going to show it splits, and it splits up finite subgroup. And so it's a lot of technicality trying to align. So when you do this integral decomposition that everybody says, well, you just do that and it follows, it doesn't follow at all, right? Because when you try to compute these things, you know, this comes with a lot of combinatorics and with a lot of new objects that, you know, basically you have to expand the theory of rigidity for factors to twisted group factors, right? So you have to develop all these results. And as far as I know, there is no technology developed there properly to handle this. Okay, so that was all. I will, sorry, I went over time.